Okay, welcome everybody to Della Pietra lecture series. Thanks to the generous support of Della Pietra family, we are able to bring top scientists from all around the world here at the Stony Brook to give us lectures on interesting topics, math and science, and many other things. And today we are lucky to have Etienne Ghys, who is a researcher in geometry, topology, and dynamical systems in Normale Supérieure in Lyon. Etienne graduated in 1978 from ENS in Lyon.
9.
Okay, 79 from Lyon. And then returned to Lyon as a researcher in 1988. And in between those days...
No, I graduated from Lille. Lille is a city north of France. And Lyon is somehow south of France. So I graduated in 79.
Start with the also, you know.
Okay. No problem.
between those days, positions in Rio de Janeiro in Brazil and in City University of New York, not far from here. And Etienne was awarded multiple prizes for both his research and his communicating science, and is known for delivering amazing lectures, explaining very complicated ideas in a clear way, which I hope for today. And in particular, Etienne is a member of French National Academy of Sciences and other national sciences. And he also produced 2 movies, at least 2 movies. One is Dimensions, and the new one, Chaos. The movie Dimensions is well known all around the world, and in 2010. The new one is Chaos, and it's 2013. So I haven't seen, but I'm looking forward to watching this movie.
Thank you.
At some point. So please welcome Etienne.
Thank you.
This is the third lecture, so I've already talked about geometry of circle for high school students, about geometry of flat surfaces to the general public the day before yesterday, and now it's intersecting and non-intersecting real algebraic.
Thank you. Actually, this is not the third lecture, this is the third and the fourth, because my purpose is not to give one talk, but 2 talks. So I will really want to discuss 2 topics which are totally disjoint. So I will speak maybe half the time on some topic, and then I will say change, and we change topic. Okay, they only chose the title because in the first part curves will intersect, and in the second part curves will not intersect. That's the only common point between the 2 parts of the talk. The first part, both will be very elementary, and the second part is a motivation. My motivation is to ask a question that I've been thinking about it for several years with no success, and that I'm hoping that maybe one of you could help me. So let me begin by the first one, intersecting curve. The story began a few years ago. I was in an administrative meeting, and I was sitting next to Kontsevich. And I do not like administration, but I think Kontsevich even less. And at some moment, Kontsevich had a subway ticket, and he wrote a theorem on the ticket, and he passed it to me. And the theorem is just a picture. So I will draw the picture, and this is the starting point of this discussion. The picture is this. So it's 1, 2, 3, 4, 2, 4, 1, 3, and then you connect the 1 to the 1, the 2 to the 2, the 3 to the 3, and the 4 to the 4. And the theorem of Kontsevich is that it is impossible to find 4 polynomials of real variables, of one variable, whose graphs look like that, in the neighborhood of 0. So let me state the theorem on the subway ticket. So the theorem is this: it is impossible when there does not exist 4 polynomials, real polynomials in one variable, all of them vanishing at the origin, and having this qualitative behavior in the neighborhood of 0. So let me put it, the graphs are like that. So f1 of x, let's say f2 of x is bigger than f4 of x, is bigger than f1 of x, is bigger than f3 of x for x positive and small. So this behavior, and f1 of x bigger than f2 of x, bigger than f3 of x, bigger than f4 of x for x negative and small. So I was amazed by this theorem, and I remember very well that in this committee there were many famous French algebraic geometers, and I showed that to them, and they were not excited. But I like this very much. This is a topological abstraction for the intersection of the graphs of 4 polynomials. When 4 polynomials intersect, the 4 branches cannot be permuted in any way. So let me prove that. This will be you will see this is very elementary. This is what is good with mathematics. You can prove new theorems with elementary tools. So how do you prove something like that? Well, of course, if you had that, you can replace f1 by f1 minus f4, f2 by minus f4, and f3 by f3 minus f4, and then the fourth one is 0. So you can assume that the fourth one is 0. So f4 is 0. Then what would be the picture? So you would have 1, 2, 3, 4, and then you would have 2, 4, 1, 3. Okay, and then you draw again the picture. 1 is going to 1. No? Yes? I lost my color chalk. Maybe I don't need color. So 2 is going to 2, and 3 is going to 3. Okay? Now, as you know, a polynomial vanishing at the origin, his qualitative behavior in the neighborhood of 0 is completely understood by the valuation of the polynomial, the degree of the lowest monomial in the polynomial. So let us look at the valuations v1, v2, and v3, the 3 valuations of the 3 polynomials which are not 0. So let's have a look at the picture. Looking here, you see that 1 changes sign. So v1 is odd. 2 does not change sign. So v2 is even. 3 changes sign, so v3 is odd. Okay? Now, looking here, you see that, let's say here, the modulus of f1 is less than the modulus of f3 for x small and positive. So the valuation of f1 has to be greater than or equal to the valuation of f3. So v1 is greater than or equal to v3. Now looking on the left-hand side, you see that the modulus of f3 is less than the modulus of f2 is less than the modulus of f1. So the modulus of v3 has to be more than v2, has to be more than v1. So v3 is more than v2, more than v1. So all three valuations should be the same, but one is even and the two others are odd. Contradiction. Okay, so I don't know about you, but I like that. This is a very interesting statement about the way in which four graphs of four polynomials intersect. Of course, this is not very much connected with polynomials. What is important is that these are the graphs of analytic functions, real analytic functions. Otherwise, you might find counterexamples using flat functions. You need valuation. Okay, so now looking at that, you might ask, can you generalize that? If you have n, yes?
Do you need V2 as well? At all?
Well, the conclusion is that V1 is equal to V2 is equal to V3. And you need V2 because V2 is not equal to V3 because V2 is even.
But if you say V1 and V3 are different, if you assume that V1 and V3 are
this I don't know. They might be equal.
You've got this thing that separates and it goes the other way.
Okay. Okay, so here's a general question. You take 1, 2, 3, 4, n. You take a permutation, sigma 1, sigma 2, sigma 3, sigma n. And the question is, can you find polynomial defining this permutation? So you have the graphs of n polynomials meeting at the origin. This defines some kind of permutation from the left to the right. And we have seen here that some permutations are not possible. Can we understand those legal permutations, those that come from polynomials? And let me explain that. Before, what?
Is that what it even?
No, okay, let me tell you something. There are 24 permutations of 4 letters. This one is not legal. Of course, the flipped one is, by the same argument, is not legal. Easy exercise. The remaining 22 permutations do occur. So in 24 permutations, there are 2 permutations that do not occur, and 22 do occur. Okay, so I call that an interchange. So a permutation, I call it an interchange if it occurs when you have n polynomials. And the question is, can you understand them? Can you count them? Can you describe them? And it is not so difficult. And one of the reasons that make, and then I understood why Kontsevich was interested by that. I understood why Kontsevich was interested by this question. But before I tell you why I think he was interested by that, let me give the result. The result is this. Let me call an the number of interchanges. And the first result is that this number is quite small. That is, when n goes to infinity, this goes to 3 per root of 2. So the number of interchanges grows exponentially of n letters. So an interchange is a permutation sigma that occurs in some choice of n polynomials. Okay, so by definition, this is less than n factorial. Okay, and the fact that this converges to a 3 plus root 2 means in particular this is a small minority in the world of permutations. Now, maybe that will give you a hint of why Kontsevich was interested by that. Whoops. An, the number of interchanges, turns out to be equal to twice Bn, where Bn is a well-known number in combinatorics, is a number of ways you can put parentheses on a word of length n in a coherent way. So you have a word of length n, like A, B, C, D, E. So here it's n is equal to 5. And you have to put parentheses in a coherent way. So it could be this, for example. And you count how many times, how many possibilities of putting parentheses. For example, B10, and this is well known, and many people have studied this sequence, but this is interesting. B10 is equal to 103,049. And what is interesting is that this number, 103,049, appears in a book written by Hipparchus 3 centuries before Christ. And historians are puzzled. I mean, why did he write this number? And it seems that there is a sentence by Hipparchus that he was thinking about the following question. Suppose you are given 10 statements. Out of these 10 statements, how many combinations can you produce? Putting and, or, implies, etc., etc. And it seems that indeed Hipparchus computed this for some reason, which is a very interesting paper in the I think, bulletin of the AMS, trying to understand how Hipparchus came to this number. What? What did you say? I don't understand.
Well, there are 10.
Oh. Okay. So let me. I will not give the proof of that, etc. But you will see it's rather elementary. You are given n polynomials, and you want to draw the qualitative picture in the neighborhood of 0. So what do? Well, you look first at the valuations of the n polynomials. If you are lucky enough that all valuations are different, then you can draw the picture. Okay. Now, if you are not lucky enough, you have groups having the same valuation. And then you go to the second jet, and you compare this group, and you compare the valuations of the difference in the second group. And then if you cannot do that, you do that to the third jet. And so you produce some kind of tree explaining the local picture. And then, so if you want to describe all combinatorial possibilities for n polynomials, this is encoded by a tree. And this tree of possibilities is exactly this number of parentheses, etc., etc. Now, why, again, this is my conjecture, why is it, why did Kontsevich write that on a subway ticket? Obviously, I think, because this is a standard example of an operad. Is it clear to you that the set let me call In is the set of interchanges. So it is somehow obvious that this family of sets is in a natural way an operad. Is that clear for you? You can insert, so here's the trick. Suppose you have an element of In. So this means that you have n polynomials. So F1, F2, and F3 in some way. And now suppose that you give me 3 more interchanges. And you will, so that's, you have here 3 polynomials intersecting. 3 polynomials intersecting. 3 polynomials intersecting. So you take this block and you insert it in the neighborhood of F1. And you take what?
These don't each have to be 3. They could be any.
Could be any number. Yeah, it could be. Yeah, you're right. It could be 5. Or anything. Okay. So if you give me an element of In and a collection of elements of ik1, ik2, ikn, you can insert the n polynomials in the neighborhood of each one of these n given polynomials. So there is an algebraic structure which comes out, and this algebraic structure is precisely the operad structure. Okay? Should I say more, or is that clear? Actually, this is just this is just
the definition of an operad.
This is the definition of operad, actually, and it turns out to be the Stashev operad.
What?
The Stashev operad, associahedron.
Don't you have an extra 2?
2 what?
Because you said.
Yeah, the 2 is a small detail that you can just rotate everything. If you have an interchange, you can completely change it.
But when you're explaining how to do these things, let's look at the right column, and you have to cut in the middle and then insert the right on the right and the left on the left.
No. You know, you take, let's say, F1 plus. You take F1 plus x to the 1000 times these ones. Okay, so you insert them here in a small neighborhood of it.
You have n right in 2 ends.
Yes. Okay. No, that's okay. That's not difficult to understand it completely. Okay. Now it is the classical. Yes.
But I don't believe that.
You don't believe that because?
That has a different number of elements. It has n factorial elements.
No. It is the Stashev operad.
Oh, with these parentheses.
Yes. Okay, let me go further. When I saw that, and when I understood that, I said to myself, how about trying to understand something a little bit more general? How about, instead of looking how n polynomials intersect, why don't we look at an algebraic curve in the neighborhood of a singular point? So let me explain that.
Always planar.
What? Planar curve. Planar curve, yeah. So when you take a singular algebraic curve or analytic curve in the plane, this is real x and y, you see that you know that the standard picture is something like that. An algebraic curve or an analytic curve in the neighborhood of a singular point is made of a certain number of branches. And each branch has two pieces. So if you take a small circle around it, around the singular point, what you see on this circle is what's the terminology, a chordal system. You see an even number of points, and they are paired 2 by 2. Each time you have a singular analytic curve, it defines for you some kind of topological object which describes the topology of the curve in the neighborhood of a singular point. Okay? Now, by the way, looking at the history of these questions, it's very interesting to see that in the time of Newton asked the question, is it possible for an algebraic curve that the curve might just stop somewhere? Is it possible for an algebraic curve to have an endpoint and the curve would stop there? Then Newton said, no, it's not possible. No proof. Then you had to wait until Gauss. Gauss in 1799, so he was a young, arrogant mathematician, he wrote the following. It seems to be well demonstrated that an algebraic curve never ends abruptly. As far as I know, nobody has even doubted this, but if anybody requires it, I take it on me to present on some other occasion an undebatable proof. Undebatable? Undebatable proof. And he never published it. So he can do it. Okay, so you have to wait until 1847, when Joseph Alfred Serret published a paper containing a proof of that. His proof is based on the idea that when you take a small circle around the origin, if you parameterize the circle algebraically as we study in high school and if you substitute your polynomial equation to this parameterization, you get an equation of even degree, and therefore there is an even number of points on the intersection of the circle. This is 1847. However, the brother of Serret, Paul Serret, 20 years later published a paper proving that the proof of his brother was wrong. Because, well, it could be a double root. How do you know that when you take this small circle, you have an equation of the even degree, okay? But this could be a double root. Who knows? And so Paul Serret said that the proof of his brother is not correct and had no proof. And I think the first proof that I consider correct is due to Ostrowski. It's 1920. And this proof is rather elaborate in the sense that it needs the Newton expansion, it needs the Newton series, it needs all this technology that you know very well. But I don't know a proof of that which is completely real, which is completely in the real domain, which is not using parameterizations of the Newton, of the Puiseux things, etc., etc. The Puiseux expansions, etc., etc.
The characteristic of a real link is even. 1970s proved that. But you complexify and
You have to complexify somehow.
you show the
Yeah.
zero and switch points. Huh? Oh, that's not allowed to use.
Well, he said real.
Oh. Ah.
Aha. Anyway, so let me come back to my question. You have two endpoints on a circle. Take a chordal diagram, I mean, you associate them 2 by 2, and you ask the question, does that correspond to some singular analytic curve? It seems to me it's a very natural question. Actually, I'm very surprised to see that the nature of singularities of curves over the complex domain has been a major theme of mathematics since Newton, Puiseux, and then for hypersurfaces, the book of Jack Milnor, etc., etc. But what for the qualitative description of the link of a real algebraic curve, nothing to the best of my knowledge. Okay, so let me give you one example that I proved. This is the simplest example when you take a circle. 1, 2, 3, 4, 5, 6. So this is a chordal diagram containing 12 points on a circle, coupled 2 by 2, and I claim that this is not an analytic singularity. And this is the simplest one. If you have less points, everything is possible.
I do not understand the statement. So you assume that these topological pictures, or you may even allow some kind of 3 or 4 arcs joined inside and only this.
No. So my claim, maybe the picture is not good. My claim is that there is no analytic curve in the plane with one singular point, with 6 branches, for which the 12 corresponding points on the circle are in this cyclic ordering. Okay? That makes sense?
You assume each branch just intersect one point.
What do you mean?
You have 6 branches.
Yes.
Just say the 2 branches intersect one point.
No. This is just a combinatorical picture. So, okay. Maybe I would need more colors. So.
How the matching is defined.
Yeah. Yeah. So the matching is defined as each point here is matched with this point with one. This one is matched with this one. This one with this one. This one. Okay. If you have a singular point of an analytic curve, it is well known by Gauss that the local picture is made out of a certain number of branches. Each branch is homeomorphic to a segment going through the origin.
For that, you've got to complexify to prove that, right?
Yeah, but this is, I take it for granted, okay? So every singular point of a real analytic curve gives me an even number of points on the circle paired 2 by 2. The 2 endpoints of the branches. Any problem, Dennis?
Wondering what the logic is.
The logic of what? I'm not claiming that I'm proving it. I claim that it's well known and easy to prove.
Right.
Okay?
It's basically a theorem about formal power series.
Yes, it's a theorem about that an algebraic singular analytic curve can be parameterized locally by Puiseux series in fractional powers, etc., etc. And you try to understand this picture in the real domain. So you look at the action of the z goes to z bar, and at the end, you get a topological picture that locally the singularity of a real analytic curve is just the union of a finite number of branches, and each branch is something like that. Okay? So if you have n branches, you have 2 endpoints on the circle, and they are paired. Is the statement clear? Isolated, I should have said isolated zero. Yeah, yeah, isolated singularity. Okay? Okay, so let me tell you why the situation is more complicated here. I see two reasons. One of them is that in the case of graphs of polynomials, the example of Kontsevich is the unique minimal counterexample. So let me explain what this means. In the case of Kontsevich, it is a fact, as far as when you understand the interchanges, it is a fact that a permutation from 1 to n to 1 to n is an interchange if and only if it does not contain Kontsevich's example. It does not contain 1, 2, 3, 4 goes to 2, 4, 1, 3. Okay? So if you have a permutation which contains as a subpermutation the Kontsevich example, it is clear that it is not an interchange. But what I'm claiming here is that the converse is true. If you have a permutation which does not contain the subway ticket example, then it is okay. You can make it. Okay? So, and of course, sorry, or the opposite. Yes. So, in the case of interchanges, the combinatorics is precisely defined by two counterexamples. If you do not find these two counterexamples inside your permutation, you're done. So you have a finite number of minimal counterexamples. And unfortunately, or fortunately, I don't know, in the case of algebraic singularities or analytic singularities, this is not the case anymore. So I can describe an infinite number of chordal systems which are not algebraic, but which nevertheless are minimal. So you cannot describe the combinatorics by checking a finite number of subsystems which are not present. That makes the situation more complicated. And the other reason why the situation is more complicated is also that the operad corresponding to that is more complicated. So let me tell you in a few words, since time is passing quickly, that in the same way as before you could insert polynomials in polynomials, in the same way you can define some kind of operad in when you can thicken the branches and insert in each branch new branches. So there is also an operad structure which is hidden there. So what I did, I
branch near a cuspidal branch.
It's topology, so you just do it. This is, I'm just discussing topology here. So for example, this picture and this picture are the same for me. Okay, this is just understanding the topology of the curve in the neighborhood of the singular point.
Before you wrote that formula, 1,000, that meant you could actually make a
Yes, but if you take one, if you take 1 million, it's the same topology. What? Say what? So it's the same thing as if you have a chordal system, and you can replace each chord by another chordal system. You can insert them, and you can make the structure of an operad on this object. And the bad point or the good point is that, of course, this is not difficult. The analogous to taking the valuation tree I was discussing earlier is to blow up. You take your singular point, you blow up, you blow up, you blow up until the thing has been desingularized. The problem is that the origin now is now a complicated link of divisors, and you have to look at these combinatorics. And the result is that I could find generators for this operad, but unfortunately, or fortunately, this operad is not finally presented. So that makes the computation of the number of legal chord systems more complicated. I don't know the answer. What I know is this. I know this. The number of, let me call it algebraic chordal with an H or not? Yes? Chordal system on 2 endpoints. The best I could do is that this is less than 35 to the n. This is the best I can do. So, what?
Better than n to the n.
It's better than n to the n, so it's certainly most chordal systems are not algebraic, but I would like to be able to understand the generating function for this this number of chordal systems, but I cannot do it. Top end of the first talk. Okay.
May I just ask a question?
Yes.
Started with this comment of Newton.
Yeah.
And you seem to say it was very difficult, and then suddenly.
No, then I said it is difficult, and indeed Ostrovsky did it, and I take it as a theorem, so I use it.
I see. So
I'm not claiming I'm proving something. No, I'm using this fact that a real analytic curve is made as the union of a certain number of branches.
who first proved that?
Ostrovsky.
Okay.
What I believe so. I mean, all earlier proofs for me are wrong. The proof of Ostrovsky, I've been satisfied by it. So who knows? Maybe somebody, I don't know. But what?
Proof didn't turn up in his notebook.
Gauss' proof claimed he couldn't do it, but he didn't publish anything.
No, but he didn't. I know he didn't publish, but there are many things that showed up in his notebooks after his death that he didn't.
Not that I know. Not that I know. Maybe I didn't spend too much time with that.
So that 35 to the n compared to the number of non-necessary.
Yeah, there are many, okay, there's many more, because the number of chordal system is total number of chordal system is factorial 2n divided by 2 to the n factorial. Okay, so this is much bigger than 3 plus. So many, yeah, okay, so there are many more chordal systems which do not come from graphs of polynomials. Okay, so I must say that this computation, this combinatorics is, I think, dirty. I mean, I wish I could make it more beautiful. I mean, I don't like this 35. I'd like to understand it better. Yeah. Oh yes, sorry. Sure. That would be very strange, you know? Yes, log.
Is there a d minus square root of 2 in the size formula also?
What do you see? The truth is that no, the asymptotics is very well known to many. The asymptotics with many coefficients is known. The generating function for an is algebraic and very explicit.
Square root of 2 as well, somewhere.
Yes. I forgot. There is a formula which is maybe I have it here. Well, I can tell you. To give you the formula. Formula is this: the generating series for an is 1 plus t plus root 1 minus 6t plus t squared divided by 4. But I am very far from having a similar formula for the chordal systems. Yes, I have a lower bound 25. Okay. Okay? So I should erase the board and start a new talk. It will be shorter. Actually, I would be very interested in, well, I should go on. For example, if you have two real algebraic curves intersecting in a plane, by Bezout theorem, we know that they intersect in n squared points. For each one of these n squared points, you have one of these pictures. I have no idea if these pictures are independent or if there could be some relationship between the chordal systems that occur at all intersection points of these two curves. I don't know.
About creating more intersections, right?
Yeah.
So there's some lot.
There should, yeah. There is a topological obstruction, you mean, yeah. But is this topological obstruction the obvious one, the only one? Okay. Now the second topic that I called non-intersection curves. In order to, what I want to do is just ask a question. And in order to ask this question, I need some preparation. And to get this preparation, I will begin by something is probably very well known, but that I somehow discovered a few years ago. And but it's probably very well known. So here's the statement. You consider a smooth function defined on some interval AB with real values. And you assume that on this interval, some odd derivative does not vanish. So you look at the 2k plus first derivative of f on the interval AB, and you assume that there is no zero of this on AB. Now here's the theorem. You consider the graphs for each point x in AB. You look at the Taylor polynomial of degree 2k at x of f. So it's a polynomial which is the Taylor expansion to the order 2k of f at the point x. So it's a polynomial of degree 2k depending on x. And the theorem is that the graphs of these polynomials are disjoint. So the theorem is no, you have one polynomial for each x.
Fixed k.
Fixed k.
Okay.
Okay, your fixed k is fixed. K is fixed. The theorem is that if you take x1 different from x2, let's say less than x2, then that is positive. The Taylor polynomial of degree 2k at x1 of f is strictly less than for every t in R. So here's the picture is this. You have your function f. You pick a point x, a, b is here, a, b. You assume that the fifth derivative of f does not vanish on ab. For each point in the interval, you have a polynomial of degree 4, the Taylor polynomial. It's something like that. I don't know. This is the Taylor polynomial over the 4 of f at the point x1. And now you take at x2, and the theorem says they don't intersect. Okay? Poof. Okay? So this not only they don't intersect on AB, but they don't intersect at all over the real line. Any problem? You don't believe me?
Should the second graph be tangent to
The X is not good.
Why it's not good? What? Oh, yeah, it's the second graph. Sorry. So x2 is here. Oh.
Change the original graph.
What?
Change the original graph.
You're right. Anyway, so x2 is here, for example. So second is. Okay, is it better? Yes?
I think you have to change the first graph.
So it's something wrong.
There's no way to get it right in the middle if you use that shape for the first graph.
Okay. So so how about erasing the picture and proving the theorem? Okay. Okay. So here's the way I like it. That's you will see. It's very easy, and I think it's interesting. So look at the map from R to the vector space of polynomials of degree 2k. Mapping each x to the Taylor polynomial of degree 2k at x of f. Okay, so it's a map from an interval to the vector space of polynomials of degree 2k. So I should be able to compute derivative of this map. Okay, let's compute the derivative. So if you remember correctly, T2k x f is a polynomial in the t variable, which is f of x plus t minus x f prime of x plus 1/2 of t minus x squared f double prime of x plus etc. plus 1 k factorial, 2k factorial, t minus x to the 2k f 2k of x. I just wrote the calculus formula for the Taylor polynomial of degree 2k. So let us take derivative of that with respect to x. Okay? So what do you get? Well, you get, how do you that? Cancellation. Everything cancels. So when you take derivative of that with respect to x, you have f prime x. And this product, derivative of product is u prime v. You see that we have f prime x minus f prime x, and everything will cancel except the last term. So what is the formula for that? You get that the derivative, let's erase this bad picture. You get the following formula. The derivative with respect to x of the Taylor polynomial of degree 2k at x of f as a polynomial in the variable t is just 1 over k factorial, or 2k factorial, f 2k plus 1 x t minus x 2k. Okay, so when you take derivative of the Taylor formula, all terms disappear except the very last one. Okay? And by definition, by assumption, I assume this to be positive. So this is positive. So if you want to compare the Taylor polynomial in 2 points, x1 and x2, you apply the fundamental theorem of calculus, you integrate that. So this is positive. This is positive. So the graphs indeed are ordered and are disjoint. Okay? Now,
for the cancellation.
Yes, I will give it in a. Well, I have only 1 second. Okay. Do I have 5 more minutes? Yeah. I should not have given 2 talks. Okay, I will explain that in a second. I just want to make a comment. This difference here is more than positive. It's positive and convex. Okay, so not only the graphs are increasing, but they are ordered in a very strong way. The difference of 2 graphs is always convex. And actually, it's more than convex, but I don't want to discuss that. Okay, so you want a geometric explanation for that? And that will be the. Yeah. I give the. No. I give the explanation in 1 minute, and then I ask the question in 1 minute. 2 minutes, maybe. Okay. The explanation is this. What is Taylor polynomial? Taylor polynomial of a function at some point of degree 2k is. Somebody is calling me. No, tant pis. So the Taylor polynomial of degree 2k at some point, you can think in the following way. You take 2k points which are infinitesimally close, and this is the unique polynomial agreeing with the function on these 2k points. So what is derivative I was computing here? Well, you take 2k plus 1 points, so that you have here x plus dx. So what is the Taylor polynomial at x plus dx? Well, it is the polynomial agreeing with the function on 2k points, but just shifted by 1. So the difference between Taylor polynomial at x plus dx and Taylor polynomial at x is a polynomial vanishing in 2k minus 1 points, so it has to be a monomial. Okay? So this idea is can be generalized in many, many ways. And I show you definitely I should not have started a new talk. Okay, so let me ask the question in a very non-natural way. I ask the question in the following way. Before that, I give another theorem. Suppose you have a curve in the plane. For each point, you take the ellipse or the conic, which is osculating as much as you can. Okay? So this is osculating to the order 5. I mean, take 5 points here, and you apply the same argument, and you look at the family of ellipses along this curve, and just in the same way that you prove that these curves do not intersect, you prove that these ellipses are nested. They don't intersect. So this is for degree 2. If you go to degree, the first significant question arises in degree 6. So let me ask a question concerning algebraic curves of degree 6. If you take a curve in the plane, you can try at each point to match it with a curve of degree 6. Curves of degree 6 depend on 27 parameters. d plus 3 divided by 2. So you have here the osculating curve of degree 6. And then you look at the curve of degree 6, which is osculating just after the one, after, a point just a little bit after. But by the same kind of argument, you can prove that the osculating sextics, they are nested. But they are only nested locally. They might intersect later. So locally, you have a picture of locally nested sextics. And this defines a local ordering, a cone structure, on the space of algebraic curves of degree 6. And my question, I'm really sorry, I'll give it and then we'll discuss that later if you wish. My question is it only a local ordering or a global ordering? Is it possible to order by some cone structure, is it possible to order the set of algebraic curves of degree 6 in such a way that when you move along a curve, the sextics are nested with this ordering? I'm sorry.
Could you redraw that so that they touch the curve and they're nested? It's not very realistic.
So you have a curve, and the picture is, but they don't intersect locally, but they might intersect in some other point.
Still not a very good picture.
This because it is impossible to draw. See? Yes.
Why can't
I'm sorry. This is generic picture. So if you take a curve in the generic curve in the plane, you look at the sextic, which is asymptotic to it. It is generically a smooth curve. Okay. And what I say is that when you move along the curve, this family of sextics locally is nested. But since two sextics intersect in 36 points, And since 36 is bigger than 27, there are, or there may be, additional intersection points far away from the locus we are looking at. And this picture, I'd like to understand it better. So I'm sorry, this is totally a disaster. I should have chosen only one topic. Sorry. Thank you very much. I'm late.
Good picture is taking us.
Well, I have some, yeah, already. Yes, yeah, it's okay. So I have a good picture somewhere. So okay, if you, what did I do with chalk? Yeah. So if you, the simplest example is you take a spiral, and for each point of the spiral, you draw the osculating circle. And the picture is something like that. And the fact is that these circles are disjoint. So, but it's, with chalk it's very difficult to draw. With a computer, you get something beautiful. You get circles that are indeed disjoint, but which are very close, and they look not disjoint. But if you look carefully, you see they are disjoint. And so they kind of are compressed in this direction. And if you go to sextic, the picture is just impossible because the compression factor is huge. And they look like intersecting, but they don't intersect.
What happens when you hit the singular point on the algebraic?
This I don't know. I was only looking at the generic situation. Yeah, I don't.
Just that you do have a specific. I mean, the next circle should conic should be inside the previous one.
So in the case of conics, this is yes. So in the case of conics, the situation is good because 2 times 2 is equal to 4, and 4 is conics depends on five parameters. So the conics are indeed nested, not only locally but globally, and that gives you a complete picture. For conics, everything is nice, but the first interesting problem is for sextics, even though I was not clear enough.
Why is 5 not interesting?
Why is what?
Degree 5. You said 6 is the first interesting case.
Oh, yeah, because 5 is odd, and then 2 algebraic curves of degree 5 always intersect. Okay, always intersect. 2 conics, no.
How about degree 4?
Because degree 4, everything is okay. I mean, the situation is okay. Yeah. For conics, you have the concept of one conic. That's I could say that. If you have 2 conics, it makes sense to say one is inside the other. My question, even though I did not formulate it correctly, is if you have 2 sextics, does that make sense to say that one is inside the other? Okay. In a projectively invariant way.
So what are good algebraic curves and bad algebraic curves?
What?
Your title, there are good algebraic curves and bad algebraic curves. What are they?
Good and bad?
Was there in the title?
No, it's intersecting and non-intersecting.
No. The title was you see the logic of my talk, which was the first part was intersecting curve. Yeah, okay, because curves did intersect, and the second part I was looking at non-intersecting curve. Sorry. Interesting and non-interesting curves.
If there are no more questions,
Thank you.